Good afternoon, everyone. I welcome you all to my presentation today. In this System Integration International Conference, I'm very glad to present our work entitled Prediction of Vitamin C using FTER-ATR terahertz spectroscopy combined with interval partially square or IPLS regression. My name is SUHANDY. I am the second year of PhD student at Graduate School of Agriculture, Kyoto University, Japan. This is the summary of our today's presentation. In the previous study, we have successfully developed a quantitative calibration model for vitamin C determination using full spectrum of PLS regression, including low and high frequency. And in the present work, we apply interval partially square or IPLS regression. So why we use IPLS? By using IPLS, we can obtain two objectives. First, we can show the mapping of the contribution of high and low frequency in determining vitamin C. And then we can also improve the vitamin C prediction with lower number of variables. And the result was very good because we successfully demonstrated that lower frequency has significant contribution in determining vitamin C using terahertz spectroscopy. And using lower number of variables, only selected subinterval we choose, we can improve the prediction performance. And both SEP and RVD value will improve. Okay, from now, let's start our brief presentation. Vitamin C. Vitamin C is one of main component of fruits, both in fresh and processed juice. So to measure the concentration of vitamin C, we usually use weight chemical methods such as calorimetry, titrimetry, and HPLC methods. Each method has its limitation. For example, using titrimetry methods has some disadvantages, such as using unstable reagents, need standardization before use, and of course, produce chemical waste. And now, recently, the use of spectroscopic-based method for vitamin C determination is becoming popular. It is simple in sample preparation, fast, and relatively low cost. Vitamin C determination using spectroscopic-based methods has been conducted by several researchers. For example, in 1993, Blanco et al. Used NIR reagent coupled with PLS regression for determination of vitamin C in pharmaceutical products. And it's followed by Yang and Irudayaraj in 2002. They use NIR, mid-infrared spectroscopy, and Raman spectroscopy for vitamin C determination, both in powder and liquid samples. And they also reported that using FTER-ATR in mid-infrared region, the result for vitamin C determination was very promising. However, it has not been reported yet. The use of FTER-ATR in terahertz region for vitamin C determination of juice from commercial or extracted juice samples. So, therefore, the objective of our study is actually the use of terahertz spectroscopy for determination of vitamin C in juice samples. And briefly, first, we will evaluate the potential use of FTER-ATR terahertz spectroscopy in measuring vitamin C in aqueous solution samples. And then, we will use the successful calibration model to predict the vitamin C concentration in commercial juice samples. And in today's presentation, I will focus on the use of IPLS or interval partial square regression for determination of vitamin C concentration using FTER-ATR terahertz spectroscopy. So first, why we use terahertz spectroscopy? So I will first introduce you the explanation about terahertz spectroscopy. terahertz wave is located between microwave and infrared wave. That's why terahertz wave has both sides of properties of electromagnetic spectrum. Like microwave, for example, terahertz wave can penetrate into many kinds of substance like cloth, paper, woods, and so on. And like infrared, terahertz wave can easily be propagated through space, reflected, and so on, using terahertz optical device. And then, while near and mid-infrared spectroscopy correspond to stretching or bending motion of individuals' bonds in the molecule, so differentially, terahertz wave utilize electromagnetic wave correspond to motion of the entire structure. So different information we may obtain by using terahertz region comparing to near and mid-infrared spectroscopy. And then, why we use ATR instead of, for example, transmitter methods? Because it is very difficult to obtain spectral information of solution sample in terahertz region, because water has very strong absorbance. So that's why we use attenuated total reflectance, or ATR, instead of using transmitter method, for example. And here, the main parts of our ATR system is the silicon prism, which has higher refractive index than the samples. So when the terahertz wave come to the silicon prism, some amount of light will reflect it back into the sample. This, what we call evanescent wave, then will penetrate into the samples. This penetration depth can be calculated using this equation. And by using this equation, our ATR system has penetration depths ranging from 1.42 to 43.48 micrometer. And this value is higher than that in mid-infrared spectroscopy. And then it is very common to use multivariate analysis, such as partial least square or PLS regression, to construct the relation between many predictors. Here is wave number and one or more target. For example, here is vitamin C. So here we have many predictors in our system. We have 110 variables of wave number, ranging from 90 to 400 per centimeter, and only one target, vitamin C. In the previous study, we use this method, full spectrum of PLS. So using these methods, we utilize whole spectrum as predictor. So we use all of the wave number as the variables, and of course, it is time consuming due to data processing time. And another important part is full spectrum model tends to be overfitting. Why? Because they use all of the wave number as variables. That some of the variables are not important and no relation with the vitamin C determination. So that's why we use these methods, IPLS or interval PLS, as one of the selected spectrum PLS in the present study. By using these methods, we can select only some spectral region which can optimize the calibration model of full spectrum regression. Why? These methods can optimize the calibration of full spectrum because we use only important variables which has relation with the vitamin C determination. And of course, it is save time because data reduction. Okay, now I'm talking about the brief explanation of IPLS regression. So in these methods, in IPLS regression methods, we will split the spectra into smaller equidistant regions, what we call subintervals, and then we will develop the calibration model on each subinterval. So we got this value, root mean square error of calibration, and also root mean square error of cross validation. And the rule is we will select the subinterval which has lower value of root mean square error of cross-validation than the average. In this study, we used 35 samples of calibration and validation, and we provide 20 samples for prediction of vitamin C with different concentration. And this is the instrumentation for our terahertz spectral acquisition. So this system works based on Fourier transform infrared spectrometer with special light source made from high pressure of mercury lamp here, and this is the ATR chamber with the ATR unit inside here, and then this is the detector. So the sample and the spectral data of the sample and also the air reference will be acquired using this parameter, 16 per centimeter of resolution and 200 number of scanning. In data analysis, we will use multivariate analysis to extract the relation between this data, terahertz spectral data, and then the concentration of vitamin C data. So when we develop the calibration model, we will use full spectrum of PLS regression and also IPLS regression with full cross validation, and we compare the results. And this parameter will be used to evaluate the quality of the developed calibration model. Result and discussion. So in the previous study, we have reported that using Savitzky-Golay first derivative spectra resulted in the best calibration model for full PLS regression. So using this full PLS regression, this model has 11 PLS factors, and when this model was tested using 20 samples of prediction, the result were obtained with SEP 2.246% and coefficient of determination for prediction 0.899. So now we are trying to improve this performance by using IPLS. So this is the result for full spectrum of the prediction. This is the actual value and this is the predicted value, and by 95% of confidence per t-test, actually there were no significant difference between actual and predicted value. Now we apply the IPLS methods. So this table shows us the results of the calibration model for 11 sub-intervals. So we choose 11 sub-intervals, and then we got this value for each sub-interval. So for IPLS model, we choose only the sub-interval which has root mean square error of cross validation lower than the average. That's why we saw this graph. This graph shows the variation of root mean square error of cross validation with the average. Here's the average. So we can see that actually sub-interval from 2 to 8 has lower or almost same value with the average. So we choose this sub-interval for IPLS model. So by using this selected sub-interval, we develop new calibration model using IPLS. And this is the result. So the IPLS model has only 6 PLS factors. It's lower, fewer than the full spectrum. And look at the SEP. The SEP is improved, better than the full spectrum, only 1.490. And of course, the coefficient of determination of prediction is higher, improved than the previous one. It's 0.952. And this is the result for prediction using IPLS model. So this is the actual value and this is the predicted value using terahertz spectroscopy. And by using 95% confidence per t-test, is also there were no significant difference between actual and predicted value. So finally, we can say that the feasibility of FTR-ATR terahertz spectroscopy combining with effective wave number selection algorithm, here IPLS, used to measure vitamin C in aqueous solution was successfully demonstrated. And then the IPLS results show that the lower frequency has better performance in vitamin C determination comparing to higher frequency. So we can say that the influence of intermolecular vibration mode of hydrogen bonding in lower frequency is higher than that of intramolecular vibration mode in higher frequency. And finally, using IPLS regression methods with selected subinterval, the prediction of vitamin C can be optimized, with SEP was improved from this value to this value. And then the RVD and RDR value will also improve. Okay, that's all my presentation today. Thank you for your listening. Any question or comment, please?
Okay, they are supposed to have the final discussion in the next week.
It's a 15 minutes presentation.
Sorry. Sorry.
I have one question. In your IPLS regression, why you divide it into terahertz region into 11 parts?
Okay, thank you for your question. Actually, this is try and error. We try to select which subinterval is appropriate, but 11 is enough, because if we divide it into smaller, for example, to 20 or to more than more small and smaller, not improve the model. So if improve, so we can continue to make smaller equidistant region to divide into smaller regions, but 11 subinterval is enough. Okay.
Just a suggestion. Your result seems to be depends on the light source, I think. Your light source is mercury lamp.
High pressure mercury lamp.
Maybe high sensitivity, lower frequency. So you should note the light source in your presentation.
Yes. Yes. Yeah. Of course. I mentioned in the previous that we use special light source for our system, made from high pressure of macro lamp. And yes, of course, this macro lamp has higher sensitivity in low frequency. But actually, in the modeling, we try to just use the data to see which part is important, and then of course by using this IPLS we can show that yes, the low frequency is better, but as you see actually okay, sorry. This one. Okay, you can see that actually this is also, we can explain that actually it belongs to low frequency, but in the first initial low frequency, maybe we can say that this region is not suitable, because maybe some of lamp or initialization so have a problem. So that's why in start of the low frequency the result was not so good, and after that it's okay, so we can use. Okay, thank you anyway for
Did you make the lantern?
okay.
No.
Oh, okay.
That's right. You
Okay. This.
Okay. Yeah.
Might be it's upright.
Okay, I see.
Or these are two. And what's this R2? R square. R square.
S square, sorry.
Slide number.
Select number, okay.
And then I think you put on the Kyoto University logo and the logo. That is every slide is not what count.
Not consistent?
Yes.
Okay.
So I think only the first slide you should put on, that is enough.
Okay. 15.
Not
17.
I think the result of the table just show the prediction result.
Table. This one.
Just show the result of the prediction.
Yes, this is the prediction.
So I think it should be moved to the next slide.
Next slide.
This is the prediction result.
Yes. Yes. Actually, this is the value of the prediction, and actually this is the graph. I mean the scatter plot.
So I think it will be good. The table move to this slide.
Okay. Thank you.
And then there should be a unit for the
Percent.
percent
I see.
in the table.
Okay. Yes, here. SEP percent. Okay.
I have a couple of comments for you.
Okay.
As you know, I'm very critical of your first presentation.
Okay. Thank
And
you.
I'm watching this presentation very carefully. And I think you have a much improvement from the last time. There are a couple of things I advise you. In the first 5 minutes of your presentation, I noticed that you did not make any in your presentation. It was very good, slow. You have not made any pause in your presentation, such as saying something that very disturbing. However, after 5 minutes, you make a lot of those mistakes again, say a lot of So that's the reason I keep telling you to slow down. One thing that you need to do is you have a lot of information in your presentation. When you're rushing it, you make a lot of those sounds. So try not to rush your presentation. The first 5 minutes you do not make any those sounds. However, after 5 minutes, you make a lot. The last sound from 11 minutes, you make a lot of those. So that's very disturbing. So what you need to do is really try to improve on that, because that's very, very annoying. Now, another thing is I find that is that you feel a lot of information in your slide. Too much information for a international conference, for a conference. A lot of those information are very basic. You do not have to address it. For example, you have a lot of work that you don't need to. For example, we successfully do this. The result is good. Those words is not necessary in the slide. Yeah, you need to simplify the slide. You have too much stuff on there. Okay.
Okay.
And also, I noticed is that you have really too much background information. For a conference, I think you can cut down the number of introductions. And I was hoping to understand why you're doing this experiment. What are your problems? How do you like to improve the method? That information should be in the first several slides, and it's not there. So it's very important to keep the audience and idea what you're going to present. Okay. Now, in the beginning, you talk very slow. That's very good. You didn't make any but at the end, when you're rushing it, you make many those. Try not to do that. And also, another thing I want to remind you is that when the fellow student asks you questions, take your time, think the answer before you answer. Because if you're trying to answer right away, the only thing we hear from you is So think of your question, think of your answer before you answer. It's okay to stop, okay to get pause. Okay?
Right.
but you are improving
Thank
from
you.
last time.
Yeah, I agree with the presentation is very good. You're a forceful speaker, so that's good. But you tend to speed up. Be careful with the laser printer, problems, breaking it around, point. And I think your emphasis in this talk is on IPLS. So reduce the first part and focus on the IPLS. Because you're basically doing a statistical technique. I think every time you have an acronym, you should at least define it once. I don't think you defined RPD. Most of the other ones define RPD.
On slide 15, I also want to suggest you like slide number 15. Watch out for the scientific number. 169.7051, too many significant number. You can reduce the number on your table significantly. Okay? There are too many scientific numbers. What you need to do is highlight the difference and just put all the numbers, tell us what those numbers mean. Okay? For example, 1, 2, 3, 4, 5, 6, 7, 8. You have 8 scientific numbers. That's way too much.
It's really good that he's taking notes. Everybody should note this. He's taking notes on the comments that are being made. That's very good.
Okay. Very high level discussion, high level solution. Okay.
It's got.
Okay, thank you very much.
Thank you very much for this.